These may look like relics of the past, but they are actually the stepping stones to a modern-day marvel. The longest bridge of its kind on Earth, and the team has just 5.5 years to build it. They'll have to battle dangerous currents, winds in excess of 170 kilometers an hour, and take on the Silver Dragon. To make the construction even more difficult, this bridge isn't spanning a river, it's spanning an ocean. China's Hangzhou Bay Bridge is the ultimate design and engineering challenge. A monster project with monster machines, and a construction zone like no other. If they succeed, it will be a man-made marvel. The dream, to bring two of China's busiest cities closer together. The two cities sit on either side of the Hangzhou Bay, a giant gulf in the East China Sea. On the south side of the bay lies Ningbo Port, the second busiest in China, with a handling capacity of more than 100 million tons. 350 kilometers away is Shanghai, the economic and financial hub of China, growing faster than any other city on the planet. Ningbo's future as an international shipping center will be fast-tracked if it can be linked to this dynamic and thriving metropolis. To make the dream a reality, engineers are designing the world's longest transoceanic bridge across Hangzhou Bay. The 6-lane bridge will cut the distance between Ningbo and Shanghai by more than 120 kilometers. But between these two mighty urban centers lies a vast stretch of ocean that until now has been beyond the reach of bridge builders. From the onset, chief designer Wang Ringgui knew he would have to work magic.
When I was first put in charge of the design and planning of the bridge, I was very, very excited. However, when I got here, the natural environment proved to be much worse than I imagined.
Dr. Robin Sham and Naeem Hussain are world leaders in bridge construction. With 60 years' experience between them, they know all too well the natural obstacles facing the bridge builders.
This area is one of the most hostile environmental area in terms of bridge building.
The decision to build sea crossing of this nature demonstrates man's desire to harness the forces of nature for the benefit of mankind.
Salt water, swift currents, and strong winds don't mix well with concrete and steel. And this is just the tip of the environmental iceberg threatening the engineers.
The more we got to know about the natural environment, the more difficult we realized building the bridge would be.
But the designers and engineers must overcome these challenges and more. At a total cost of nearly 12 billion yuan, the bridge represents the future of the region's economy. But a freak force of nature could see the dream over before it's even begun. Hangzhou Bay is home to the Qiantang River tidal bore, a giant wall of water that forms when extreme high tides, carried on the strong currents from the bay, force their way into the narrow river mouth. The power of this water is so great, it causes the river to flow backwards and produce the giant wave. The Hangzhou Bay tidal bore is known as Silver Dragon, and every year, in the middle of the 8th lunar month, it wakes up. Reaching speeds of 40 kilometers an hour and heights of up to 9 meters, it's the largest and most spectacular bore in the world. And every year, hundreds of thousands of tourists come for a front row seat. But this natural wonder is unpredictable and dangerous. To date, the mighty dragon has claimed the lives of at least 100 people. And this remarkable phenomenon could claim the bridge before it's even started. In a bizarre twist, it's not a case of if the bridge can survive the dragon, but can the dragon survive the bridge? Before the designers can begin, hydrologists need to know what they are dealing with. The bridge could alter the flow of water through the bay, destroying the Silver Dragon and a multi-million-dollar tourist attraction. They undertake extensive studies of the Qiantang River's flow, as well as the tides and currents in the bay. Then replicate these findings with a scale model of the bay, complete with a prototype of the bridge.
The current for the model and the actual current are very similar. The experiments give us results on the effect of the tide and direction of water flow.
From these experiments, Jiang works out exactly where the foundations must go to minimize the bridge's effect on the currents. The result is a bridge in harmony with the currents. 36 kilometers long, winding out in a giant S shape across Hangzhou Bay.
This will enable the water to run smoothly under the bridge, minimizing the impact on the hydrology and the tidal bore.
The S shape won't interfere with the yearly dragon tide, and it will have another life-saving benefit.
If you make a straight bridge, a long bridge, all the driver sees is a black tarmac in front of him. And that can be quite monotonous. In fact, it can be downright dangerous because of sheer boredom of driving a long length.
After 10 years of planning and more than 50 separate studies on environmental conditions, the design is complete. The world's longest transoceanic bridge gets the go-ahead. But the project gets off to an explosive start. Beneath the surface of the ocean floor, right in the path of the bridge, is a dangerous deposit of gas. Just as deadly as the dragon's breath, the gas could stop the project in its tracks. The dream to connect two powerful cities, Ningbo and Shanghai, and propel the entire region into a period of unprecedented development. But constructing a 36-kilometer-long bridge across this turbulent sea won't be easy. Before construction even begins, the team finds out that Hangzhou Bay harbors an explosive secret that threatens the future of the bridge. Surveys reveal large natural gas deposits 50 meters under the ocean floor, right in the path of the bridge.
When planning the bridge, we never consider the possibility there would be natural gas here.
The bridge design calls for thousands of steel piles to be driven almost 80 meters down into the sediment. But with a minefield of natural gas below the seabed, it's a recipe for disaster.
My first reaction was maybe this was not a suitable location to build a bridge.
Driving piles into the gas deposit is extremely hazardous. The uncontrolled eruption of gas could undermine the bridge's foundation. A stray spark could ignite the gas and fuel a catastrophic explosion. Each time the team drives in a pile, it could spell disaster. Construction is put on hold until they can find a solution.
We were very worried. If, say, the natural gas problem couldn't be overcome, it would then bring harm to our construction and also the lifetime of the bridge.
The greatest threat comes from pockets of gas that are stored at the highest pressure. These pockets can pop like a balloon, erupting with devastating force. But after careful analysis of the gas field and consultation with leading experts, engineers come up with a solution.
We call it controlled gas release. We pick the most concentrated areas of the gas. Then we drill holes down there, releasing the gas.
Small pipes are drilled into the gas deposit and fitted with pressure valves. The gas is slowly released until the pressure is low enough that the gas no longer poses a risk to the bridge. It's an ingenious solution that enables the engineers to go through the minefield, not around it. And the project is back on its feet. To build the world's longest transoceanic bridge, they must first drive 6,000 steel piles into the seafloor.
For the foundations of the bridge, we mainly depend on the steel piles. The steel piles for the bridge foundations are not replaceable.
Each pile must stand up to being hammered 80 meters into the rocky seabed and endure decades of exposure to salt water. It's a tall order, and there's no room for failure. To ensure success, they decide to custom build special factories near the construction site to make these extraordinary piles. Here, sheets of steel, 22 millimeters thick, are rolled into giant tubes, 1.5 meters wide and almost 90 meters long. Each tube is arc welded twice as it forms. First from the inside and then from the outside. They use a special copper-plated alloy to weld the steel together. Copper is a superconductor. It increases the temperature of the welding wire. When finished, the copper simply cracks off. Weighing in at close to 70 tons, each colossal pile takes 40 minutes to roll and weld. These are the longest and strongest steel piles ever used in a construction project in China. But these mighty steel pillars will be reduced to rust and rubble if nature gets its way. The piles stored on shore are rusting before they even make it to the water.
For this particular bridge, its design life is 100 years. What that means is the material that we use should be able to last 100 years with the least amount of maintenance and the least amount of inspection.
For the piles to last the test of time, the team must protect the steel from the elements. The process is costly and time-consuming. First, the piles are run through a machine that blasts the rust from their surface. Then they continue into another mammoth machine that coats them with an anti-corrosive preparation called fusion-bonded epoxy. To seal in the epoxy, the coating is heated to a sizzling 250 degrees Celsius. The temperature is crucial. Any significant drop and the seal will fail. Workers must constantly check the temperature using infrared sensors. But the team is confident that the piles are now ready for whatever Hangzhou Bay throws at them.
The steel piles designed by us will last for 100 years.
To speed construction, the team is building the bridge from the south and north sides of the bay at the same time. These separate stages must join with absolute precision. The placement and alignment of the piles is crucial to success. Traditionally, bridge builders use visual surveying to pinpoint where a pile must go. But with a bridge 36 kilometers long and an environment prone to torrential rain and heavy mist, the engineers will need to find another option. GPS, or Global Positioning Systems, use satellites to calculate positions accurate to a matter of centimeters. In the case of the Hangzhou Bay Bridge, GPS reference stations are set up on land. Experts from Trimble Navigation design an integrated GPS system for the bridge builders. Base stations on either side of the bay communicate with orbiting satellites to create a triangulated reference grid. Each pile is given a unique fixed address based on its latitude and longitude. When it's time to place the pile, GPS receivers on the pile driver locate that fixed address.
On the piling barges, they have two GPS, which actually reference to the base station out on the shore. So this power barge is able to navigate to the power positions, roughly, and once it gets close to the point, anchor is dropped and it's winched to its exact position. And once it's there, the power will be dropped. It really revolutionized the way construction work is being carried out, really changed the way we work.
With this high-tech GPS system, the two ends of the bridge should meet precisely. 2.5 years after the approval of the design, the first pile is sunk into the sediment. But with thousands of piles still to go, there's no time to waste. To drive 6,000 piles into the seabed, they'll need a massive sledgehammer mounted on a monster ship. This enormous floating pile driver has been purpose-built. The piston drives the pile into the seabed with a force of 250 tons per meter. With each tremendous impact, the 28-ton hammer rams the pile deeper and deeper into the seabed. It takes more than 2 hours to drive in each giant 90-meter pile. The bridge is starting to take shape. But the piles are only the first phase of the bridge foundation. The team must now construct concrete piers to support the bridge. And once again, the bay's corrosive environment spells trouble.
For bridges of this scale, there are basically two materials, steel and concrete. Concrete, by its very nature, will actually require less maintenance than steel. But concrete also, we have found, does not have durability unless it is done properly.
It's not the concrete itself that's vulnerable to the environment. It's what's inside, steel reinforcing. Normal construction concrete is quite porous. Water gets in through the pores of the concrete and makes its way to the steel reinforcing. When salt water hits steel, it causes the steel to rust and expand, pressing the metal against the concrete from the inside. Under this increased pressure, the concrete starts to break down and the pier rots from the inside out. The concrete piers on the Hangzhou Bridge are reinforced with multiple steel rods called rebar. To seal thousands of tons of rebar with a protective coating would be too costly. The only solution is to make sure the steel doesn't come in contact with the salt water. The engineers need to develop a stronger, less porous concrete mixture.
When we started, we had no former examples to look back on, so we made thousands of different formulas. We tested them out and picked the best.
The exact composition of the oceanic concrete developed for the Hangzhou Bay Bridge is a carefully guarded secret. But engineer Liu Naisheng can reveal one key ingredient.
We add soot to the concrete mix to fill in the spaces and link up the substances. It will increase the strength and enhance the anti-corrosive ability of the concrete.
The soot is actually a special volcanic ash that they add to the mix. Another key component of this 100-year concrete is a corrosion inhibitor. a chemical compound that slows down any reactions between the salt and the steel. Getting the right concrete formula took time, but it is well worth the effort. The hours spent in development will pay off tenfold once the bridge is complete.
If we use concrete as opposed to steel, that means that the maintenance cost then gets reduced, because concrete by its nature does not need repairs and repainting as you would do with steel.
Using clever chemistry and trial and error, the team has conquered the elements in the water. But as the bridge rises upward, engineers face another powerful force of nature: typhoons. To bring the prosperity of Shanghai to the port of Ningbo, engineers are constructing a 36-kilometer-long bridge across Hangzhou Bay. For the project to be a success, the huge container ships that use Ningbo port must be able to pass under the bridge. This will require giant spans 450 meters wide and 45 meters high over the deep water shipping lanes. But these towering bridge sections create a whole new set of problems when the environment is factored in.
Another major design challenge was to design this bridge, the navigation spans, for typhoon wind conditions.
Hangzhou Bay is home to some of the most violent storms and typhoons on the planet.
Since construction for the bridge started in November 2003, a 2-year time span, we have encountered 11 typhoons.
Typhoon winds can reach speeds in excess of 170 kilometers an hour, causing extensive damage to everything in their path. The enormous spans needed for container ships to pass under Hangzhou Bay Bridge will be prone to wind. Here, the distance between the piers is so great that the weight of the span must be supported by cables from above. And cable-supported bridges are especially vulnerable in high winds.
Cable-supported bridges are very flexible. What that means is that due to wind traveling across them, like an airplane wing, they will tend to oscillate. Wind tunnel testing and other criteria have to be taken into account in designing for wind stability.
To find a design that could stand up to the extreme conditions in the bay, the wind engineers built numerous models of the bridge, then subjected those models to the typhoon-strength winds the real bridge will have to endure. Getting the design right is crucial. If they don't, the results could be devastating. The Tacoma Bridge in Washington State in the United States is a classic example of what can go wrong. The bridge was nicknamed Galloping Gertie because from the moment it was finished, it was unstable. But in November 1940, high winds hitting the extremely flexible bridge caused a bizarre twisting motion. This unusual pattern grew steadily worse until finally the cables broke and the bridge self-destructed.
That is what we need to ensure will not happen on a bridge. So we make the bridge by shaping its edges and making its shape such that it will be aerodynamically stable.
After extensive wind tunnel testing, the engineers come up with their final design. A cable stay system supported by a 202-meter-tall A-shaped tower at the south end of the bridge, and two 187-meter-tall diamond towers at the north end. The cables will support the giant spans, and a triangular shape will increase the stability of the towers in high winds. The result? Navigation spans stiff enough to resist typhoon-strength winds. But coming up with a design that can stand up to the environment is not the same as building it. High above the raging currents of Hangzhou Bay, the workers at the bridge must battle the extreme elements every day. It's not work for the faint-hearted.
The workers need to overcome a frightened state of mind. Most of our workers hired to work around these parts have no experience of working near the sea and have never experienced typhoons before.
It's not just the workers' state of mind that concerns the team. Workers' safety and the completion of the project are in jeopardy.
The construction program is 5.5 years long. That may seem reasonable, but every year the weather window suitable for construction is only around 200 days. So just to think we have to squeeze all construction activities into 200 days a year, that is a great challenge.
The team has to take decisive action to ensure the safety of the workers and keep the project on schedule. Because when severe conditions take hold, work at sea comes to a halt. They come up with an ambitious plan. If it succeeds, it will create a safe work environment and keep the project on track. The plan? To build the world's longest sea bridge on land.
Once we move the fabrication process and build the bridge on ground, so to speak, and try to find a way to erect it up there in the air, we would have removed a lot of headache, and we're also less prone to the forces, the elements of nature.
When severe weather conditions halt construction at sea, prefabrication can still take place on shore. Vast prefabrication factories, stretching as far as the eye can see, are set up on both sides of the bay. These manufacture the giant girders required for the construction.
What that means is that you get really good quality product built in factory conditions, under controlled conditions. They can be made in large segments, then be brought to site and then assembled.
Traditionally, prefabricated girders are made in a series of pieces and are assembled together at the bridge site. But to reduce the time at sea, engineers use a clever technique on a scale never attempted before. The giant girders will be cast in a single mold.
The technique has been used previously. First time it was used was on the Taiwan high-speed railway. But those were much smaller units. But what is interesting here is that this is by far the largest unit in the world.
These massive girders are up to 70 meters long, 16.5 meters wide, and weigh a staggering 2,200 tons. Lying on top of the piers, they create the tabletop structure which will support the road. To make the largest girders, 200 tons of steel rebar is tied and welded together. It takes 65 workers just under a day to produce one of these massive steel skeletons. Once complete, the steel frame is transferred to the mold using a giant crane. The drive mechanism uses a unique synchronized rotation system, allowing it to turn on a dime. The crane maneuvers into position and carefully lowers the steel frame into the mold. Engineers check the exact positioning of the frame and make final adjustments. Each girder soaks up a whopping 830 cubic meters of concrete. To prevent cracking, they pour the concrete in one go using 4 pumps and a constant supply of concrete. It's an impressive feat of coordination, and takes 150 workers 8 hours to cast one girder. It's going to take over 1,000 prefabricated girders to complete the 36-kilometer-long Hangzhou Bay Bridge. But building the bridge will require moving these giant jigsaw pieces out to sea. It's an engineering obstacle course, and to succeed, the team will have to take bridge building technology to a whole new level. Building the world's longest transoceanic bridge across China's Hangzhou Bay is a monumental task. To overcome extreme weather and complete the bridge on time, the construction team have developed some radical solutions, including building the enormous girders on land. But weighing in at a colossal 2,200 tons, the girders are the Goliaths of the prefabrication process. Moving them from the factory to the construction front will be a logistical nightmare. Deep water on the north side of the bay means that construction materials can only be transported to the work front by boat. For the workers and their supplies, this doesn't present a major problem. But to transport the giant girders, they're going to need some truly awesome lifting power. This mighty machine must be able to position the enormous girders accurately onto the 40-meter-high piers, while coping with the swift currents of Hangzhou Bay. The answer? The Tianyi, a giant floating crane powered by a 4,800 horsepower engine. Tianyi means number one in the world. At 93 meters long and with a displacement of 11,000 tons, it's easy to see why she got the name.
The capacity of this machine can reach 3,000 tons. The lifting height can reach 53 meters.
She will need every ounce of her incredible size and power as she takes on the bay. As the Tianyi carries the girder out to sea, the mists create a false sense of calm. But beneath the surface of the water, the battle has already begun. Extremely swift currents rip through Hangzhou Bay, the fastest, reaching a staggering 5 meters per second. At that speed, a boat has to do almost 10 knots just to maintain its position. Even the fishermen who call the bay home struggle with the fast-moving water that changes direction with every tide.
In my opinion, the biggest challenge is overcoming the fast currents. If you take a boat to the fast current zone, after you've seen the current, you would feel quite scared.
Out in the bay, the crew struggles to maneuver the giant ship into place. The rapidly moving water is a real menace when the girders must be lifted up and onto the piers with millimeter accuracy. Anchors hold the Tianyi in place. Then the crew winch the ship to the exact position. The crane can now lower the girders safely onto the piers. Once in place, the workers release the cables from the girder, freeing the Tianyi. But the Tianyi can't be used on the other side of the bay. On the south shore, the water's too shallow. Tidal mudflats extend for 70 kilometers along the coast and 10 kilometers out to sea. At low tide, virtually nothing can move in this quagmire, except the odd clam harvester. Even at high tide, the mudflats are a no-entry zone for large construction. The team can't afford to get bogged down at this stage. They'll have to come up with a creative solution. Once again, the engineers rise to the challenge. To install the enormous girders, the team develop a specialized truck, stronger than anything that has come before, and a machine that defies gravity. And it all starts with a whole lot of wheels. The TE 1600 is a 640-wheeled vehicle specially designed to carry the giant girders from the factory to the construction front.
By carrying the 1,430-ton girders, this machine broke the world record. Before, the record for the world's heaviest transporter girder was a 900-tons girder in Italy.
To achieve this record-breaking task, the TE 1600's 640 wheels are spread over 4 separate vehicles. Joined at the front and back by giant support beams, each vehicle has 160 wheels arranged into groups of 4. The load on each wheel group is automatically adjusted through an integrated hydraulic system to ensure that the weight is evenly distributed at all times.
If a tire pops, other tires next to it can share its weight capacity, so it won't cause the whole vehicle to tip over.
This is very important, as the TE 1600 uses the unfinished bridge as an access road across the mudflats. If the girder were to fall off here, it would be stuck in the mud forever. Although separate, the 4 vehicles drive as a single rigid unit. Multiple sensors relay information to onboard computers. The computers use this information to adjust the speed and angle of each of the 160 wheel groups to ensure the 4 parts work as one. The TE 1600 can reach a top speed of 4 kilometers an hour when fully loaded. At that speed, it's not going to win any races. But this slow and steady mechanical millipede is set to revolutionize the building of long-span bridges.
This particular design is unique to this particular bridge. And I have to hand it to them. They have done it, and other people will probably use this technique elsewhere for other bridges.
But this monster millipede will need an equally impressive partner if the mudflats are to be conquered completely. And that's when the next machine steps in, or rather, steps out. The LGV 1600 literally walks on thin air to install the girders. Once the girder walker reaches the distant pier, the rear movable leg rolls to the end of the previously installed section. And the front movable leg rolls across the open span. The lifting winches move to the front to balance the walker. And the back leg lifts up. The millipede enters with its load. The back section of the millipede drives forward. The rear leg of the walker folds down, and the winches move back to pick up the girder. Steel rods from the winches are secured to the girder. Once in place, the girder is lifted off the millipede and carried to the front section of the girder walker. Now that the weight is distributed to the front again, the back leg lifts up. The millipede drives off to get another load. And the existing girder is lowered into place. Using this technique, they can install 2 to 3 girders each day. And slowly but surely, one span at a time, they will bridge the giant mudflats. After 3 grueling years, the piles are all in place. Most of the piers are complete. And as the girders are positioned, the bridge begins to reveal itself.
As an engineer, I can visualize the bridge. You can see the columns coming up now. You can see that it will be long. The curve of the bridge is there. It virtually disappears into the mist. There's a kind of mystery at the other end of the bridge. You wonder where it's going to land.
But there's still a long way to go before the bridge finally comes together. The team will encounter more typhoons. Winds and currents will pound men and machines. But it will all be worth it if they can finally build the world's longest transoceanic bridge. Just 3 years into construction, the Hangzhou Bay Transoceanic Bridge is fast on its way into the record books. To conquer the extreme environment, engineers have expanded the scale of existing technology. And when that wasn't enough, they've invented some radically new technologies. But what is perhaps the most amazing aspect of the Hangzhou Bay Bridge project is the speed of the construction. They achieved this by building the large bridge components on land and then transporting them to the construction front. The scale is truly awesome, and the rate of construction nothing short of superhuman.
I'm sure, like many projects, to those people who worked here, it would be a major achievement, probably with some people in their lifetime. And also it provides an example for other countries to follow that if there's a will, there's a way.
The bridge is being built out from the shore on both sides of the bay at the same time. Finally, the huge northern navigation section, with its twin 187-meter-tall diamond-shaped towers, will be linked to the southern navigation section and its 202-meter-tall A-shaped tower, designed to carry the weight of this wide-span section of the bridge. When the pieces finally come together, the team will have the satisfaction of knowing they have built the world's longest sea-crossing bridge.
Since the bridge started in 2003, I've been on site supervising the construction. In my opinion, it's like raising a child. I, as the parent, am very happy to see it grow daily.
36 kilometers of engineering brilliance. And it all culminates in the bridge's crowning glory, a spectacular service island built on a giant platform in the middle of the bay. An architectural masterpiece housing hotels, shops, restaurants, and a world-class conference center. The futuristic island will also feature a 136-meter-high observation tower. Shaped like a giant pearl, the tower will give travelers a bird's-eye view of this monster bridge. It's the largest bridge project of its kind ever undertaken in China. When complete, 52,000 cars will use the bridge every day. But that figure will grow to nearly 100,000 cars by 2027.
Once the bridge is open for traffic, I will definitely drive on it. I want to see for myself that we achieved the objectives set for this bridge.
When finished, it will have used a phenomenal 767,000 tons of steel and 2,400,000 cubic meters of concrete. The Hangzhou Bay Bridge is scheduled for completion in 2009, just in time for Shanghai's hosting of the World Expo in 2010.
If anyone is flying out from Shanghai, they will see this bridge. It's massive. And it will definitely have a place in the history of bridges as one of the first bridges which has been done of this sort of length.
For the millions of people expected to visit Shanghai, the Hangzhou Bay Transoceanic Bridge may well be their first glimpse of China and one of its man-made marvels.
接下来，打造一座规模大小、超越整个西半球的桥梁。建筑巨擘，接着播出。